Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It is my pleasure to announce today's speaker, Bertrand Meyer. I think I don't have to introduce him in great detail because all of you are familiar with his work on object-oriented programming and software engineering. Bertrand is currently a professor at ETH Zurich in Switzerland, and he is visiting us during his sabbatical for about 3 weeks, so he will be here until Thursday next week. If you want to interact with him, please do so. And today he will talk to us about simple and safe concurrent object-oriented programming scoop. Please.
Thank you very much, Peter. It's indeed a great pleasure to be here. I mean, that's a received formula, but in this case, in this particular case, it's true. I must say I'm here largely to learn. So well, maybe I have to deliver something in return, but I have much more to learn from you than you may have to learn from me. I'm actually here for another 2 weeks, so it's Thursday next week. No, not, well, Thursday. The week after next, and I'm of course quite happy to talk with absolutely everyone about the exciting things that you do, and possibly about some of the things that we do. So today I'm going to talk about some of our work. It's work that has been going on, at least on paper, for quite some time. It's not really new ideas, but they have taken some time to mature, and in particular to be implemented. So the origins of the model go pretty far back, but it's only recently that we have had an implementation and a way really to show that this is not just a pie in the sky and theory, but that it can work. So of course it's trying to address the Holy Grail. I think most of the or much of the industry today has realized that the future is in concurrency. It's becoming really a cliche, and I'm going to skip that part about how important it is to be able to go from sequential programming to concurrent programming. So this is my part of the quest to the Holy Grail. One thing that I should mention right away is the big deficiency of this work. It's probably better if I mention it before you discover it. And it's really a big limitation on this work, especially in a Microsoft context. Microsoft is very interested about performance, and rightly so. Maybe sometimes as a user of Microsoft products, I wish Microsoft were even more concerned about performance. But in the case of concurrency, it's even more important, because in the end, we don't do concurrency because of all the beautiful problems that this raises or all the elegance of concurrent programming. We do concurrency because we want more power, more from our machines. And the work that I'm presenting today is really focused on something else. It's focused on being able to reason about our concurrent programs in almost the same way as we are reasoning about sequential programs, or at least in ways that are as close as possible to the way we have been used to reasoning about sequential programs. So of course it's in a concurrent context, but the big question mark, and I really want to be very open about this, because otherwise it would be dishonest. The big question mark is whether we can use this approach, which I think is quite appealing intellectually in terms of reasoning about programs, and still get the performance improvements that we are entitled to expect from going from sequential to concurrent. So I should mention this big question mark from the start. And of course, it's my task to resolve the question mark, to answer the question, but we have not done it yet. So one way to start is to present a very simple piece of code, which I'm very soon going to turn into a piece of specification. In fact, there is not much code, as you can see. This is the code, right? And it's not extreme. It is efficient, that's for sure, but it's not very detailed. So the point, of course, here is more the specification, and indeed, if this is part of some class which describes queues, for example, bounded queues, which could be implemented in some way, represented graphically here. What I really want to do is to think about it as a client, as someone who is going to write code that uses this. I really want to think about it without having to know anything about the implementation. So I think of it in terms of a signature, maybe a header comment which helps me because the flash is weak, and a precondition and a postcondition, all of this together making up a contract. So what the contract says is actually very partial, even with the limitations of the Eiffel contract language, which is basically Boolean expressions. I could have written a little more. The contract says, don't try to insert into a queue if it's full, or to put it positively, only insert if it is not full. And as a result, you will have the guarantee that it's not empty. And the queue is called B. And there would be the place where I said that we could have written more is here. Obviously, we could have said more. Even without addressing frame issues or complicated things, we could have expressed properties like the oldest, the newest element will now be V, something like this, but it's not relevant to this discussion. What's important is that we have this contract and we can reason in terms of it. When I try to explain contract ideas to students, I always say bad news are also good news in the following sense. A precondition is bad news, right? It tells you what you have to do in order to be permitted to use a certain operation. But it's also good news because in any half-decently written piece of software, the precondition tells you all that you have to satisfy in order to be guaranteed the result. So in that sense, bad news is good news, and what it means in particular is that if I'm a client, again, knowing this particular piece of software from the outside and through only through the official specification as shown on the left with this part grayed out, then I know that if I satisfy the precondition before the call, then I'm entitled to a proper satisfaction of my goals, in particular to the postcondition and in general to correct execution of the routine. So for example, I could test, and if I do this, then I'm guaranteed, of course, that when I call put, the precondition will be satisfied, so all will be perfect in the best of all possible worlds. So this is sequential programming. And of course, as we all know in concurrent programming, this is not true anymore, because between the time of course, as we go from sequential programming to concurrent programming, our nice little queue might have turned into a buffer. What's a buffer if not a queue that is shared between different clients in a concurrent context, right? So now we have a buffer, and between the time I've tested for is full and the time I confidently rely on this knowledge that it's not full to do my put, my insertion, anything can have come in and destroyed this beautiful setting that supposedly guaranteed the correct handling of my request. So this is concurrency 101, and anyone who has ever tried to program a printer that alternates between various jobs and found that because of a concurrency error or synchronization error, a few lines from one job appeared mixed with a few lines from some other job, knows this the hard way. So the problem, though, is that the traditional notions of specification that we are used to break down, right? It's very difficult to admit that this notion, for example, that preconditions are correctness conditions just doesn't work anymore. Because if it's a correctness condition, then if you ensure it before you call, then you should be entitled to proper handling. And this is just not the case. So it's very difficult to accept this. And it took me a long time to accept it, but it's inescapable. And I've come to believe that it's one of the central issues of concurrency. It's usually not what you see discussed in presentations of concurrency, but I think it's quite central. And in a few moments, I'm going to suggest a solution to this dilemma in the form of a reinterpretation of what preconditions in particular mean. So this is the part that probably is not needed anymore. The world is concurrent. And of course, everyone's told, even the New York Times nowadays is saying that programming should be concurrent, so it's probably true. To put it differently, in the 90s there was this joke about object-oriented programming, which said that object-oriented programming is like teenage sex. Everyone says they're doing it, Not many are really doing it. I'm talking about the 1990s, and so those who are doing it are not doing it very well. Apart from the middle statement, this is exactly concurrency today, right? So the question that I'm asking, which is not necessarily which is not the only possible way to ask the general question of concurrent programming, is can we bring concurrent programming to the same level of abstraction and convenience, it's forbidden to laugh, as sequential programming. So is this true that well, yes, to a certain extent, we have reached a certain level of abstraction and confidence in sequential programming. For example, through introduction to techniques like structured programming or object technology, we're used to having higher level abstractions. We have techniques that avoid bugs, that have transferred the task to implementation, that in some cases at least lets you do stuff that you couldn't do before. I'm thinking in particular of things like garbage collection on this side, which really enables you to program in a completely different way. Remove some restrictions, adding restrictions in both cases. I'm picking here on two significant improvements over the past 40 years in programming methodology. There are others, but these are among the most significant. And one of the things they have done in order to achieve these goals of improving abstraction and the level of confidence that we have in our programs is to add restrictions, paradoxically, to someone from the outside. There's a well-understood mathematical basis, whole semantics in one case, and abstract data types in particular in the other. But many people who have no clue about that mathematical basis still benefit from the ideas, and in particular from the increased level of abstraction. You don't need to know what a whole triple is to understand that structured programming, even in a very narrow elementary sense of the term, one entry, one exit, simple control structures and so on, helps you reason at a more abstract level, in particular at a less operational level, in a less operational way. This is perhaps one of the biggest advantages of these advances. It's that, if you think, for example, of the GoTo, when we used to program with GoTos all over the place, you cannot really reason about a program without turning yourself into a computer. Because you are here, maybe something is not going the way you want, so you're debugging something and you have to think, okay, I've executed this before. Oh no, but wait, I could be coming from up there, or I could be coming back from down there. So basically, you think very operationally. And the common element behind all these advances is that they bring you one level up from this low level of abstraction, and they enable you in particular to reason less operationally. So this is what has happened on the sequential programming side. So it used to be messy, it's still hard, otherwise there wouldn't be so many people working on the programming at Microsoft Research and many other places. So it's still hard, but there have been key improvements. And of course omitted many design patterns, many others which would deserve to be listed here. On the side of concurrent programming, on the other hand, it used to be messy, and the big lesson is that it's still messy. Basically, we're still doing concurrent programming for the most part with the techniques invented by Dijkstra, but pre-structured programming Dijkstra, right? The Dijkstra of semaphores of 1968 or so. And there have been a few improvements, but not significant. So the development level is still that of the 60s and 70s, and this is not going to function for forever. We are going to have to bring up concurrent programming at a conceptual level similar to that of sequential programming by following a similar progression if we are to make concurrent programming as widely available as it's slated to be. And this seems to be almost inevitable. So the reason it's inevitable, of course, is what you read everywhere about us programmers having to worry about multi-core and about networking and the world not being sequential anymore. So this is an area which used to be the province of a few experts working on operating systems, on networks, and so on, and which now is of concern to everyone. So how do we address this? How do we go about the provision of a good, solid basis for concurrent programming? I'm not going to go into all the details of Scoop, and I'm actually spending on purpose some time on these motivational aspects, because to me this is the most important part. So this is not the introduction, if you like. You may think that I'm still in the introduction. I'm not. Well, you know, our whole life is an introduction, but this is other than in that sense, this is not. What I would really like to try to do is to explain the rationale behind all these Scoop decisions, so that you can follow the line of reasoning. And of course, if at some point you diverge, it's important to know which one of the assumptions you don't like. So I'm starting so the general framework is very simple. We ask the following questions, which is again not necessarily the only way to ask about about concurrent programming. The question I'm asking is, let's start from what we know and understand. And for this, I would say object-oriented programming as practiced today, or maybe in that case, as it should be practiced, as the rest of the world should practice it today. But we can start with a common basis of object-oriented programming as implemented in the major approaches. So this is something that we more or less, on a good day, understand reasonably well. And let's, yeah. I'm coming to this, actually. I haven't bashed Milner yet, but that's coming. So the question is, how do we start from this and make the smallest reasonable extension that will give us concurrent programming as well, without losing what we already have? Okay? So that's one way of asking the problem. So someone else could say, we don't care about sequential programming as it's practiced today. We want the best possible concurrent programming environment, period. Okay? But this is the question I'm asking here. So when you start from that basis, many people have had their revelation, their Damascus moment, looking at objects and saying, oh, this is almost concurrent already, or maybe not almost, this is concurrent already. So this is Milner's Damascus moment, although I think it was in Glasgow or a place like this, which is not as nice as Damascus, but or as sunny as Damascus. It was at an ECOOP conference. So it's just not true in the following sense. And, the reason objects seem to be naturally generalizable to a concurrent context, to processes in particular, is that, like processes, objects have a state. They're autonomous entities which communicate with other entities of the same kind. So this is the kind of superficial, feel-good initial idea. But then it breaks down. And the reason it breaks down is very simple. It's that objects typically do not have a scenario. They do not have their own engine which tells them what to do minute after minute. An object is there to serve requests from other objects, from the clients. If it becomes a process, if it becomes an entity with its own scenario, then immediately you run into mismatches, because A wants to do certain things, B wants to do certain things, and at some point A needs B, but B may not be at a point of its life where it's ready to accept a request from A. So then you run into difficult synchronization issues, all the traditional issues of concurrency made more difficult by object-oriented constraints. And when you start adding inheritance, then it becomes hopeless. So more precisely, it becomes a very good thing if your goal in life is to produce papers, because you have inheritance anomaly and all kinds of things for which you can have papers, T-shirts, conferences, journals, and so on. But in practice, okay, it seems very difficult to go further. So the idea is going to be a little different. It's going to be to accept objects as they are. And when I say objects, I really mean the entire object-oriented framework, classes, inheritance, and so on, and to see how, as mentioned a moment ago, we can extend it. Now, before I start giving you the idea, the exact principles, I'd like to shock you, or perhaps, or at least to give you an idea of the style of Scoop by presenting the solution to the dining philosophers, to the kind of cliche dining philosophers example. And the reason I'm showing this is, of course, that it makes Scoop, I believe, shine, because essentially this is all there is to the solution. Of course, you need some supporting machinery to create the objects and so on, but the algorithm is here. So let me try to explain it, even though I have not shown the scoop mechanisms yet. We ignore the inheritance part for a second. What a philosopher does at each step is to think and to eat. And there's no synchronization, at least no explicit synchronization, because one of the basic ideas that we're going to see is that when a client needs a lock on certain objects, it just passes them as arguments. That's one of the key mechanisms. And the idea is that you wait until you have been able to lock all the arguments, at least all the arguments that represent what we're going to call separate objects, meaning objects that are handled by a different processor, by a different thread of control. So what this really means is that, as in the case of the two technologies that I mentioned earlier, structured programming and object-oriented programming, many of the things that you would normally have to do yourself are transferred, their responsibility is transferred to the implementation, to the compiler, because of course we have all the problems of reserving multiple resources and not getting into deadlocks and such, but this is all taken care of by the implementation, because this says reserve for me these two resources left and right, and so you are sure that when it succeeds you have these two resources. And the trick to making this happen is to declare L and R, which correspond to left and right, the formal arguments of eat, as separate, meaning they're elsewhere. We're going to see this in detail. The other thing that I think is interesting in this example is that instead of considering mechanisms like inheritance as our enemies, as difficulties to fight, we actually treat them as our allies. After all, inheritance, I know that not everyone likes inheritance, but for those of us who like inheritance, we like to think of inheritance not as something complicated on which we can give questions in the exam at the end of the year, but as something that actually helps us produce code that is more elegant, more reusable, more extendable, and so on. So, and here is the same thing. So what do we do? This is, I'm assuming a class process, which is not predefined, but it's a library class, and a process describes any object with a scenario, actually referring to what I was saying a moment ago. So this idea of an object with a scenario is not something that's built into the model. It's something that you can program, which is also another reason to shoot for a more modest mechanism than active objects. So a process is an active object. And its character, I'm not showing the class here, but the class has a procedure live, and live is a loop which executes various things. First it starts with setup, then it loops on step, and maybe there's a close down or something at the end. So all that we really have to do is to, in a descendant, is to implement step. So that's why there's no loop here. The loop is taken care of in the live procedure of process. And of course, I'm facetious enough to take advantage of the Eiffel renaming mechanism to rename the setup of process as getup for a philosopher with a little pun. So, okay. So this is just to give you an example of the kind of simplicity that one can achieve. And I've seen quite a few, as I'm sure you have, quite a few implementations of the dynamic philosopher's problem, in particular with mechanisms like Java threads and so on. And it's very difficult to achieve this kind of simplicity if you have to handle the priorities, the protocols, and the locking and so on manually. Okay, so now for the core of the mechanism in its principles. We start with a very elementary observation, which is that to perform a computation is to apply certain actions to certain objects using certain computing mechanisms which we call processes. Okay. No one's going to get a Nobel Prize for saying this, but we have to start somewhere. What's new in object-oriented programming is the relationship between actions and objects. We attach the actions to the objects rather than the other way around. What's new in concurrent programming is that we now attach importance to the processors. in sequential programming, we know there's a computer. I mean, there's an electrical engineering department. We know there are people who deal with these things. You know, we know there's Intel and AMD, but we don't. We kind of pretend they don't exist, right? Because there's one processor, and we just rely on it. In concurrent programming, we now are going to have several processors. So this is a very simple way of describing, and a naive but correct way of describing the difference between sequential and concurrent programming. When we are talking here about processors, we don't necessarily mean a physical machine. It could be a thread, which is what I'm going to use for the examples and what the current implementation uses. It could indeed be a CPU. It could be an app domain as in .NET. It could be anything that has the ability to execute a sequential set of instructions, a set of instructions sequentially, to be more accurate. So if we come back to the example that I showed a moment ago, typically those two elements of code, the client and the supplier, are going to be handled by different processes. This is what makes the whole thing concurrent. Now, let's try to see how we can retain some of the beauty, meaning some of the simplicity of reasoning about programs that we have in a sequential world. So the basic rule for reasoning about object-oriented programs is something like this. Now, here, there are people here who know much more about this than I do, but I believe the basic framework is correct. This is the basic rule that even, as I said earlier, people who don't know anything about the formal aspect that they use implicitly. So the idea is that if you want to prove a property of a certain call, or at least to understand a property of a certain call, proving it or not, then it suffices to have the corresponding property of the body of the routine. So we have a routine R, which is being called on X, and body sub R is the body of the routine, of the method. Pre sub R is its precondition. Post sub R is its post condition. I'm using here an ad hoc notation with this prime because I didn't want to load the slide with symbols too much, but the priming simply represents the substitution of actual for formals. Okay? So basically, if I've proved the property of the body, that from the precondition I'm going to get the postcondition, I can deduce the corresponding property of the call, where we have to substitute not only the actual for the formals, but also we have to take the X, the target, into account. And the extra property that we take into account for the proof of the body is the invariant of the class, which basically reflects that we are programming in an object-oriented way, not in Pascal or something like that. So what's interesting about this, beyond the details, is that if I have a class,
Well, you know that doesn't work.
I was kind of fearing that you would raise your hand at just this particular point, but so yeah.
Because of reentry. So you're assuming non-reentry.
Yeah. Right. So with enough simplifying conditions, indeed, the big advantage of this is that if you have a class with n routines, you essentially have to prove n things to prove your class correct. The correctness of the class is defined by the n properties for each one of the routines. Now, if we are in a concurrent context, let's assume that we allow various clients to work at the same time on the same object, which is probably what you want to do for performance. Well, the whole thing breaks down completely. You have so many possible interleavings that any such linear reasoning, if I can call it that way, is impossible. So some people, and this is where, of course, you get data races and other pleasures of late nights. So there are people who would say, well, that's life. You have to handle this in the best possible way. The decision that is taken in Scoop is to say this is far too complicated. If it's too complicated, we don't understand, and if we don't understand, we don't want to do it. So the first rule is going to say we are not going to allow any overlapping whatsoever of method calls on a given object. So at any particular point in time, on any particular object, at most one operation will be proceeding. So this means, in particular, relating this to the notion of processor introduced a few moments ago, that there's going to be a mapping between objects and processors, so an n-to-1 a function, if you like, between from objects to processors. Every object will be assigned to a certain processor which is responsible for executing all the calls to routines on that particular object. So this is a big restriction. It may seem unduly constraining, but it's, in my opinion, part of the price to pay to continue applying some of the same reasoning mechanisms that have proved their mettle in a sequential context. The next observation about what differentiates sequential from concurrent programming is related to the fundamental operation of computing. If you're doing object-oriented programming, one of the nice things about the approach is that fundamentally at runtime computation consists of just one kind of operation. Method call, message passing, routine call. That is to say, call a certain operation R on a certain object that we know from its name X, possibly with arguments. So this is what our object-oriented programs do again and again and again at execution time. So it's a very simple computing model in the end. That's part of the attraction of object-oriented programming. It has the following property in a sequential context. It's synchronous, right? In the sense that if I have some instructions before, say previous, and then I execute x.r, where R is again going to perform some operations of its own, then the client will not proceed with its execution with the operations called next here until the call has terminated, because you have one processor, so it can only do one thing at a time. Now, if we move from a sequential to a concurrent context, this is not the case anymore. Actually, the whole idea of having concurrency is that in many cases you don't want to have to wait if you don't need to. So if the client and the supplier have different handlers, remember that I define a handler as being the processor in charge of handling all the calls on a particular object. If they have different handlers, then we, in many cases, do not need to wait for the execution of R to have terminated in order to continue. In fact, we don't even need to wait for the execution of R to have started, right? As long as we can somehow log the request and preserve the order, which is, of course, very important to be able to reason about these things, we don't have to wait for the call even to start. So we're going to see exactly under what conditions we will wait, and because at some point we will need to wait, right? Because, for example, if we're doing this, x.r is probably because we need some of the results. So at some point we will need to wait for these results. By saying this, I've almost given you the resynchronization rule, but it's coming formally in a second. So we are going to have two different semantics as a result. One that waits, one that doesn't wait. If we have the same processor, it's synchronous, it waits. If the client and the supplier are handled by different processors, then it's asynchronous. It doesn't need to wait. If we, on the other hand, so far, the syntax, this is the Eiffel syntax, but it's the same in most object-oriented languages. In most cases, in both cases, the syntax was the same. That's not right, of course. If we have two different semantics, we should have some indication in the program that this is not the same thing. So the decision that was made for Scoop is to say we are, in that case, going to declare the target, a small x in this example, as separate. So if it's not separate, it means synchronous. If it's separate, it means asynchronous. So what does separate really mean? Separate means elsewhere, foreign, alien. I don't know where it is. Could be a Tokyo, it could be in the next building, or it could be another thread on the same machine. I just know that it's not me, or that more precisely, it might not be me. So little clarification here. The separate qualification in Scoop means potentially separate. Because the reason for this, to make a small digression here, the reason for this is very simple. A may know B as separate. B may know C as separate. So from the viewpoint of A, C is separate. And then C may know D as separate. Same thing, but perhaps we're actually cycling back to ourselves. And we don't know this statically. So in fact, someone who I think is foreign might actually be local. So that's going to be the rule. Separate means potentially separate. And let me use the term local for non-separate. Local means guaranteed to be handled by the same processor. That is going to be the convention. Okay, so this is the first fundamental semantic rule, the synchronous versus asynchronous calls. It immediately raises a number of problems, and I'm going to describe all, but let me describe one of the most typical. It's the problem of traders. So traders, as you know, are those people who pretend to be one of us, like me here. I'm a Microsoft employee, but I might be a trader. Who knows, right? I'm a Microsoft, not employee. Microsoft, well, something. So a trader is someone who is claiming to be one of us, but in fact he works for the enemy. And so, stopping the metaphor, stopping my flowery metaphors for a while, this would be the case with this non-sep here. Okay? Non-sep is declared of type T. Sep is declared of type separate T, so at some point it might be attached, it might be representing some object which is running on a different processor. And then let's assume we allow assigning a separate to a non-separate. Then, of course, the next thing we know, we could be calling a routine on non-sep, and we think it's a synchronous call. But in fact, it cannot be a synchronous call because non-sep has a different handler. So a rule is needed to disallow this kind of thing, to disallow traders. Non-sep is a trader, and I'm not giving the formal rule here, but the basic rule says that you cannot assign from separate to non-separate. Okay? Now, the reason I'm not giving you the rule is that this is only one of the rules. In fact, there are a number of situations that can produce traders, and there used to be, until recently, a whole set of maybe a half a dozen ad hoc rules that basically disallow these things. And this was, of course, not very pleasant. And I forgot to mention at the beginning, but you may have seen the name of Piotr Nienaltowski, who was one of my PhD students until last year, who did a thesis on Scoop, and he cleaned up the whole thing and replaced all these ad hoc rules by annotations in the type system, which give a much more consistent and elegant way of defining what's allowed and what's not allowed in order to guarantee disallowance of traders, non-appearance of traders. So, and I'm not giving you the details of the type system here, but it's all in his PhD thesis and in a couple of papers that we've published since then. The next rule is one that is very shocking to just about anyone who sees it for the first time, and I must say to many people who see it for the nth time with varying n. But I believe it's right. It also shocks me at times, but the reason it's shocking is that it seems to be very restrictive. And again, I'd like to explain why the rule is like this. It's there to avoid confusions in situations like the one represented here. I'm pushing a certain element on a stack, then I do something else, maybe, but it doesn't touch the stack, or at least I hope it doesn't touch the stack, right? And then I want to have the top. So obviously, I believe that y is A. It's this element that I've just pushed. This is, of course, a kind of absurd example, but it's an abstraction of many real situations. And in a concurrent context, again, this might not be true because anyone else could have fiddled with the stack in between. So we could say, well, too bad. If you want to protect your stack, lock it explicitly. So there have actually been variants of scoop, like a development that was done a few years ago by John Potter at the University of New South Wales in Australia, where there were explicit instructions like hold my stack, then, and then you do whatever you like and you're sure you have it. Okay. So it's possible to do this. Being perhaps of a more disciplinarian nature, at least for this kind of thing, I always thought that this was still too risky, because it's so easy to write things like this and confuse yourself, lead yourself into believing that nothing will have happened in between, that this is the kind of situation where we have to essentially protect us against ourselves. And this, of course, is debatable, but it actually seems to be not as restrictive or painful in practice as it might seem at first. So the rule is very simple. It's that you are not permitted to have a call such as the one we had a moment ago, any one of these. You are not permitted to have such a call with a separate target, my stack dot something, my stack being separate, unless my stack is a formal argument of the enclosing routine. So this means that if I want to do stack, it's called stack now instead of my stack. If I want to do stack dot something, stack must be an argument of the enclosing routine if it's separate. Okay. And of course, this goes with the semantic rule, which appears next, which is that if we have a routine call with separate arguments, it will only execute when all the corresponding processors are available. So argument passing becomes a locking mechanism. This explains the eat of left and right, which we had in the earlier example. Right? So we could, in a situation like this, for example, if I want to do something like buffer.put, well, where buffer is separate, this is only permitted if buffer, again, is a separate argument of the enclosing, is a formal separate argument of the enclosing routine. So I'm going to have to do this, right? Put of my buffer in order to do anything to it. I'm going to have to reserve it. So this is also a place where performance could take a big hit, because for anything that you want to do on a separate object, you first have to grab it. Now, it's not like you're grabbing the entire database, for example. You might just grab one object that gives you access to the database, and where you can register your actual request to the database in the database example. But still, you need to have exclusive access to that object at some point. And again, the dilemma here, or the trade-off, is between the highest possible performance that you want to get. Did I do anything? I said this was shocking, but I didn't know it was that shocking. Yeah. You want to get the best possible performance. On the other hand, we also want to be able to reason about these things. And you see where we are heading now, because when we have essentially locked every separate object that we need to reason about, to work with, then it's almost as in a sequential case. Not quite, but almost. And I'll give you the whole rule in just a few moments. So you have the choice. So then you're forced to decide, because this is going to be invalid as written. So any one of these calls has to be in a routine of which my stack is a formal argument. So then you make the decision. Do I need to keep the lock throughout, in which case they will be in the same routine, or do I not, in which case you can just write two little wrappers, so two separate wrappers. So you do end up writing quite a few of these wrappers. But so we could have this hold instruction. I mean, the jury is still out, right? I'm not saying that this is the answer for the next 2 centuries, but you know, we have tested the hypothesis again and again, in particular in seeing how much it pollutes how much, if at all, it pollutes our writing style, and it doesn't too much. It really seems to hold well in practice, but the jury is still out. Okay, so we need a rule for resynchronization. In a situation like this, if this is all in a routine of which x is a separate formal argument, we're going to start off x.f, we're going to start off x.g, start off on another processor, maybe y.f. So when do we actually resynchronize, right? So the answer is sometimes never. This could be the boot procedure. So it just starts a whole set of processors and then it's done its job, right? So it doesn't need any answer from these. So this is, to me, is an important example because it shows that we don't always need to resynchronize. So we should only resynchronize or have a mechanism for this when we need it. So the rule here is an idea that is very simple. It's we resynchronize when we need to. And when do we need to resynchronize? It's when we need a value from one of these things. So if and only if later on we have something like x.sum query, I'll explain the term query in a second. When we need a value from x, then of course at that point we have to wait for all the previous computations that have been logged to x to have finished, because otherwise we couldn't have a meaningful value. So a little bit of Eiffel in here. Eiffel distinguishes itself from most object-oriented languages since Simula by not making a clear-cut distinction between methods and fields. So a query is a member of a class, a feature as it's called in Eiffel, that returns a value. But it could be implemented as an attribute, meaning as a field, by lookup, by memory, or it could be implemented as a function. Okay? So that's what query means, and here again we don't make the difference. So anytime we need a value from x, we are going to wait. End of Eiffel digression. So this is called, this comes from work by Denis Caramel, who's now in Nice. And he calls it, so there are two names, lazy wait and wait by necessity. I tend to prefer lazy wait, but it's the same thing. And it's really his original idea. That works, which works quite well with the rest of the mechanism. Okay, so now we come back. And this is essentially going to be the final point in the presentation of the mechanisms. We come back to the question that I asked at the beginning implicitly of what do contracts now mean. This is the second part which has been known to cause shock. So Rouston, you did order the ambulance and reanimation and oxygen tank and so on. Good. So I think the example I showed earlier, which was just a bit simpler than this one, is enough to suggest the unpleasant, but in the end I think inescapable conclusion that the standard interpretation of preconditions as correctness conditions just doesn't work in a concurrent context. So if they're not correctness conditions, what can they be? Well, the suggestion here is to say they are wait conditions. Now, this is the part which is probably going to be even more shocking, because we have, in this particular example, we have two arguments, as you can see, buff, which is separate. Sorry, I should have said this is separate. Forgot it. And, well, integers are not separate, as you can imagine. So we have two preconditions, one separate, one non-separate. What I call a separate precondition is a precondition which involves a call of the form a dot something, where a is separate, like we have here. So in this case, we are going to have, at least at first sight, a different handling of, or different semantics for the two clauses of the precondition. The first one is a wait condition, the second one is a correctness condition. Now, the way we look at it now, we meaning in particular Piotr Nielatowski, because our views evolved significantly as a result of work on his thesis, is that they're both wait conditions. Okay? So in the second case, so even going back to a completely sequential setup, if you're saying require n positive, completely sequential program, well, this is still a wait condition. Okay? But there's a kind of, in that case, static analysis. You've heard about static analysis, right? The static analysis is powerful enough to determine that either n is positive now or it will never be positive. So the compiler can basically extract this particular rule. Let me ignore this now and go back to this example. The compiler can actually determine that the second clause, even though formally it's a wait condition, is one that can be resolved in a different way. In particular, if we are using contracts as we are in the current state of the Eiffel technology as debugging mechanisms, that is to say, we can turn them on at runtime for testing and debugging purposes, then we know that we can basically generate different code for the first clause and the second clause. The first clause is really a wait condition. The second clause, if it's not satisfied, indicates a bug. So if buff is not full, this is not a bug. This is just that we came in early. We have to wait a little bit. We have to be patient. If v is equal to -3, we can wait long. We can wait very long, but the -3 is not going to turn into something else. So the compiler should be smart enough to understand the difference between those two cases. So what I just said, if you like, is not that important. It's a way of it's more intellectual polish on the difference between the two semantics. It's just an artificial way of saying, in the end, maybe it's not two different semantics. We only have one kind of semantics, namely waiting, and correctness is a special kind of waiting. Soundness is a special case of liveness, so to speak. So this is the approach that we're taking now. Okay, so preconditions become wait conditions, and the full synchronization rule, complementing the one that was given earlier, is that a call with separate arguments waits until the corresponding objects are all available. So that was the previous rule, and although it doesn't say it here, obviously we are going to lock all these objects for the duration of the call. And in addition to this, we wait until all the preconditions hold. This is actually quite pleasant in practice because it gives us a simple synchronization mechanism. Okay? Give us the equivalent of conditional critical regions. So this we've seen. So the general idea is that, at least from an intellectual viewpoint, it doesn't change things much in practice. But from an intellectual viewpoint, sequentiality is a special case of concurrency. Wait semantics always applies, and wait semantics boils down to correctness semantics for non-separate preconditions. A smart compiler can detect some cases, and other cases will be detected at runtime. I think I'll skip the part about post conditions, maybe because I don't want to finish too late. So I can come back to post conditions maybe if there's any question about it. So the rule that we get is actually disappointingly simple and perhaps a bit disappointing. I'm not convinced this is the latest, this is the best we can do. But this is the one we have at this point. And it's essentially the same one that we had before in the earlier slide. The only change is this can't here in two places. Can't means controlled. So a can't is the part of the subset of the argument sequence that is controlled. What is a controlled expression? And this is something that is known statically. It's anything that is attached and handled by a processor on which we have a lock. Let me explain both. Attached means non-void. So Eiffel now has a mechanism known as attached types, which was quite openly influenced by the spec sharp mechanism for non-null types, and which makes it possible to declare that a type used in the declaration for a variable will or will not be permitted to have the value void. No. we actually hijack this mechanism a little bit. It's something that I skipped. Since we, in some cases, small digression, in some cases it's useful to pass a separate object as argument when you don't want to lock it. So for example, assume that you don't do anything on it. You don't do an A dot something. You just want to pass it on maybe to someone else. So then it would be bad to have to lock it. Actually, it would be a source of deadlocks. So if you just want to pass it on, to pass the reference without locking it, well, in that case, the formal argument should be declared as non-attached, detachable. And it's all consistent, because if it's detachable, we cannot do A.F on it. So in order to do A.F on it, we would have actually to reserve it, to lock it. So it all falls into place. So a controlled end of digression. A controlled expression is one which is attached. So we know that we need the object, and which is handled by a processor on which we have a lock. So we can only assert things. This is what this rule says, is that although we have to do the full proof, I mean the hypothesis of the rule, the top part, is still the same as before. We still have to prove the routine exactly as we did before. We're actually going to deduce less. We prove as much, but we deduce less. We can only reason about things that we own. Okay? So this sounds right to me. The problem is that maybe there are things we cannot prove with this. Maybe it's not strong enough, because of course we are renouncing any knowledge whatsoever about things that we do not control. And although I have not found it, I have the intuition that we could say more. But that's the rule at the moment. There's one part of the mechanism that I need to mention, although I don't have any slides on it. It's the dual, so-called dual mechanism. This is a mechanism designed to loosen the grip of a holder that has extended its welcome. So the rule is this. Let's assume that we have that we have a holder that has a certain object and a challenger that wants it. So normally, if the holder has the object and the challenger wants it, well, because there's locking, the challenger waits. That is the default situation that we have seen so far. However, there are cases in which you might want to give priority to the challenger. It's like you're driving on the freeway and there's some VIP that comes and everyone is pushed aside. So that's the idea. So in some object-oriented concurrent mechanisms that we've seen, there's a notion of express message, a message that can be handled. It's exactly that metaphor that I just gave. We put aside we put the challenger aside. We kind of squeeze in another call, and then we resume. So anyone who has ever tried to do any proofs knows that this is completely, or even just semantics, that is really excluded. So what we want to do in the Eiffel context is that if this kind of situation arises, then we are indeed going to stop the current challenger, but by causing an exception. That's the idea. Because then that forces the challenger to handle that exception. If it doesn't handle it, it's going to be killed, which is okay. It's okay to kill all the motorists that were driving to the airport. It's not okay just to put them aside and let them continue, because this might induce some inconsistencies in our reasoning, and it's much better to kill the public than to let logical inconsistencies get in. So the idea is that there are library mechanisms which are called normal service, and that's for the challenger, normal service and immediate service. And for the holder, it's going to be retain or yield. So if the holder has said, sure, you're so much, I'm willing to be interrupted, then the holder is going to get an exception. If the holder has said retain, and the challenger says, I want immediate service, then the challenger gets an exception. And I forgot about the last entry. But the basic idea is that we can break a lock, but only by causing an exception. And exceptions in Eiffel are closely tied to the contract mechanism. So when you get an exception, it's not just a try-catch. You actually have to do something about either admitting your failure or trying again to achieve your contract. This is a side aspect of the mechanism, which, however, can be very important in practice, because especially in an operating system for a situation, you don't want to be blocked forever by, say, some driver writer that has not done his job properly. Okay, so perhaps let me illustrate, show you a couple of executables. So just to there's nothing really extraordinary about these examples, but they show that the stuff is actually running, even though these are already several years old. So the Dydic philosophers was here. This was done already at least 4 years ago by a student on an earlier implementation, but it still runs. So this is exactly the program that I showed. This is something that is always hard to believe for me, because this program was in one of my books, and when I write a book with a program in it, I don't really expect the programs to run, but actually he took it exactly as it was, and it put in some GUI, and well, it runs. Okay, and we can make some philosophers more greedy. Sorry. And well, there's no deadlock. I've just proved it, right? It ran for 20 seconds. And the last example that I'll. No, I'm sorry. This was intended to be a bad joke. That I proved it by showing it for 20 seconds. No, okay. Let me answer this. Let me actually answer this as part of open problems in just a second. And so the other example, again, it's straight out from the book Object-Oriented Software Construction. It's a design for an elevator system that is fanatically object-oriented. So everything is an object, and everything has its own processor. So even every button in every cabin is a separate object. And well, the code is in the book, and if I can show the elevator quickly, we actually built it. We built it in hardware using Lego Mindstorms, but then every visitor who came to our office always wanted to touch it, so I'm not sure it still runs. So I can. These are the floor buttons. These are the cabin buttons, and it's more fun to create lots of elevators and do it in a simulation way, in a simulated way. So we've done it in particular to make sure that it will scale up. For example, our first implementations used busy wait, and as you can imagine, it didn't scale up very well. But we run it without the user interface with something like 10,000 elevators and hundreds of thousands of threads, and it does scale up. So that part of the performance doesn't worry us too much. Okay. Just to finish, so the implementation has been built on top of Eiffel threads, which internally uses either POSIX or .NET threading. So the examples that I showed were running on .NET, not just because I'm here. Actually, I would have shown the .NET implementation even if I were not here. So it was built initially as a library in order to avoid mixing language issues with concurrency issues. And now we're in the process of integrating the whole. So the next step was to build a preprocessor so that you don't have to write calls to this library scooply, which became a bit tedious with time. So we have a preprocessor which enables us to write scoop code exactly as I showed it, and then it's turned into Eiffel with library calls. the dual mechanism is in the process of being implemented, but it's not available yet. Everything that we have is available for download. The current developments are integration into the actual language and compiler, into the development environment, Eiffel Studio, a closer performance evaluation. We have used there's not been, as far as I know, any industrial use of Scoop, but we have had extensive applications in courses. We have used Scoop for teaching concurrent programming 3 times now, with some really interesting student projects, including hardware, including things like robots and such. So we have that level of scalability at least, but not actual industrial use. There remains quite a few open problems. So this is the answer to your question. We have a number of ideas about deadlock, but we don't have a consistent theory about deadlocks yet. This is definitely a big thorn in our side, which we need to remove. We are looking into ways to lock a little less. In this respect, software transactional memory ideas are very interesting, but this is just a very superficial observation at this point. We want to integrate a transaction model. We have a pretty good semantics for what's there now, but we need to have a more complete semantics. As I said, I'm not totally happy with the rules that we have, and we want to extend this framework to not just threads and processors, which is what we have done so far, but real distribution and web services. So that's what we have, and again, the assumptions are very clear. We're not necessarily trying to have the most complete, the most performant concurrent implementation in the world. We are starting from the side of programming methodology, structured programming, object-oriented programming, systematic development, and trying to see how much we can retain of this and still be able to participate in the fun games of concurrency.
Thank you very much. I knew it was dangerous to admit to Bertrand that I have reserved the room for 90 minutes, and I'm grateful that he still left a few minutes for questions. So I will bring the microphone because this talk is recorded, so if you have a question, please speak into the microphone.
My question is about the processors that execute different operations. So if we have about the processors and the separate or separable objects that they work on. So from my understanding, each object is assigned to some processor and stays there forever. What happens with a function, say it, takes 2 separable forks, each one of them being assigned to different processors? Which of the processors will be executing this it function?
So you have a function that takes two arguments, each assigned to different processors.
Yes.
And then.
And from my understanding, if there is a processor, if there is an object, if there is a separate object, yeah, then you need to access it on the processor that's assigned to it.
Yeah. So what's going to happen is that if you have f of the elevators are still running happily around. Good. I'm not going to disturb them. So you're going to write, say, f of a and b, where a and b are both separate but handled by different processes. So this call, remember, since it has separate arguments, it's going to wait until it can reserve, until it can lock both of these objects. And then let's say that this is actually A and B are both of type separate something. Okay, and then at some point it does A dot operation 1, and later on it does B dot operation 2. So these operations are going to be executed by the respective processors of A and B, which actually is okay in that case because we have locked these processors. Okay?
If for that precondition, if both A and B are mentioned in the precondition of F, then suppose that they are joined by a conditional OR. Do you lock both of them still? or do you only lock the ones that actually participate in the evaluation of the precondition?
Give us, we lock it. You give it, we lock it. We lock everything. Yeah. So they have something like A dot pre1 or B dot pre2. Yeah. We lock everything.
Other questions? Well, then let's thank the speaker again. And as I said, Bertrand. Thank you. Bertrand will be here until the 21st, so feel free to contact him.